I'm Dr. Patricia Shaw, and this term we're going to be looking at the Valiant robots, and I'm going to be introducing that. As part of the Valiant robots, we will be looking at transitioning from block-based programming to text-based programming, but don't worry about that. We'll take you through it nice and steady. So, what is the Valiant robot? Well, it's actually quite an old robot that we've essentially rebuilt and repurposed inside. Um, but we've added lots of nice new sensors and various features to it. So this is the robot we can see on the right hand side. It's got a battery inside. There's an Arduino Uno. So we'll be continuing programming the Arduino. There's a big LED on the back, really nice bright LED. There's also a large LDR or photoresistor from Tinkercad. There's a couple of infrared sensors, and on the top we've got an ultrasonic sensor, and that ultrasonic sensor is actually mounted on a servo, so not only can the robot turn around, but the servo can also turn to look from side to side. There's a speaker in there that we might get a chance to play with during this term, and there's also a couple of motors, so there's a couple of wheels under there that are driving it around. Now, don't worry about the pins too much, but we will be going through and playing around with various different components listed here. So the LED, the LDR, the ultrasonic, hopefully the servo, and of course the motors as well. And so we will be taking you from the block-based programming that you've been doing previously and gradually transitioning that to text-based programming. And we'll be working with Tinkercad again. And what we've done is we've built a circuit that matches the inside of the robot, the Valiant robot that we'll be using. So we can see the Arduino here. It's connected to a battery. The size of the battery isn't actually important here. And we've got our ultrasonic sensor, the LDR, an LED. This is the servo that we've got, and it's actually, you can just imagine the ultrasonic being mounted on top of that so it can rotate around. We've got our piezo buzzer here for the sound. And then we've got two motors here. These yellow blocks here are the motors. It's a two-wheel drive robot. And this black box here is actually a chip that's acting as a controller for those motors and enabling us to program and tell the motors what to do. So for the code, we'll be using something called Arduino C as a programming language, a text-based programming language. Some of you might have had a look at it last term, seeing the blocks and text side by side. But by programming the text directly, we can actually do a lot more with it. And in particular for these robots, it'll allow us to connect to the robots directly and make use of the serial monitor to take readings from the sensors. But with text-based programming, we can also write much more sophisticated and interesting programs. We can do a lot more with those programs. Actually, the blocks just don't quite give us the scope, the ability to write. And so we'll be looking at this text-based programming, specifically Arduino C for the Arduinos. But there's also a lot of text-based programming languages out there, and you may have come across some of them or heard of some of them in the past. Commonly heard of one is Python, which we might have a look at later on in the year, but not straight away. So let's have a look at what the very basics is to start off with. So on the left, we've got our blocks, the familiar on start and forever blocks. And on the right, we can see the equivalent of these in the text-based programming. So it's almost a direct mapping from one to the other. So on start becomes this void setup round brackets. And then inside this on start block, we would actually be able to clip in multiple other instructions that we wanted to have. And you see it's got a sort of a start and an end point to that. And in the text, that's indicated by these curly brackets. So the end of the on start has got a curly bracket, closing curly bracket, and the start of it has got this opening curly bracket. And we've got the same for the forever loop. just to be aware that these brackets always pair up. So make sure you've always got them in pairs. So we've got a pair of the round brackets and pairs of curly brackets. And so for the forever loop, that maps onto this thing called void loop. So it's going to be this void loop is going to be doing exactly the same as this forever block that we had previously, and again there's space for those instructions to go in between, and they clip in between these curly brackets. So everything that we'd want inside our forever loop goes in between these curly brackets. That's our functionality. I should say I will be introducing quite a few new terms, new words and terminology this term. If anything isn't clear, then do remember to ask on the Wednesday afternoons, but hopefully we'll take it through nice and steady. So between these curly brackets, and you can find these curly brackets on the keyboard, typically just to the right of the P key. If you press Shift and the square bracket, then you'll get the curly brackets. Okay, so what have we actually got here? Now, this setup and the loop are actually what we call, well, they are referring to particular functions, and these are the names of those functions. Now, these particular ones are very special in that they have predefined names that we have to use. So we have this setup function and this loop function. These are preceded by special keywords. So void is a keyword. I will explain what void means later on, but don't worry about it for the time being. Just, if you can, accept that when we're writing this on start, that actually becomes void setup round brackets. And then we've got the two curly brackets. And same for the forever loop, void loop round brackets. And then these two curly brackets. Now, when we're running our programs, the computer tries to read everything that we write, but sometimes it's actually quite useful to have some notes or comments, as we call them, in our code to actually help remind us what it is that it's doing, or to help others understand what our code is doing. So comments are really, really useful. And actually, when you look in Tinkercad, you will see comments in the code. And these comments are ignored by the computer. So we can actually write whatever we want to within those comments without having to worry about the computer trying to run those. And actually, sometimes if something isn't quite working properly, then commenting out a line, as we refer to it, so using these double slashes at the start of a line, we'll just tell it to ignore the line that we think is probably causing the problem, so we can check what's going on in our program. But we do have two different types of comments. The most common is this single line comment, and that's the two double forward slashes at the start of the line or before the text that you want to have commented out. So it could actually be partway along a line, and it will just ignore everything else for the rest of that line. The other type of comment is this /* multi-line comment. So it starts off with a /*, then you can put in whatever text you want and it can cover multiple lines, and then it finishes with a //. So enclosing that text inside it that you don't want the computer to be processing. Again, it can be a handy tool for debugging or modifying your code quickly, just to comment out that section rather than deleting it. So you can then add it back in again easily at a future date. So two very handy types of comments to tell the computer just to ignore those, but without actually having to delete the code itself. So let's have a look at a bit more code. Now, you may notice when you start to do the text-based programming that some of the words are in different colors. And that's what we call syntax highlighting. Now, syntax is a special word for describing the structure, the language, the features of the language that we're using. And some editors, like Tinkercad, try to actually make the code a little bit easier for us to read as humans by highlighting different types of words with different colors. Different editors might use different color schemes, but in Tinkercad we can see a little bit of colour here, and so it's useful to just be aware of what some of those different colours mean. So we can see a couple of single line comments up at the top, and they're in a sort of brownish type colour, and there's another single line comment here that actually starts part way along a line, and again that's in the brownish colour. This void keyword is marked up in a slightly purplish colour, so we can see that that's recognised as a keyword by the computer. And you may or may not be able to see that this number 10 here is a slightly greenish colour in Tinkercad, just to say it's been recognised as a number. You may notice some other syntax highlighting as we go through, but generally that is what it means. So let's start to have a look at actually getting our program to do something interesting. Well, we'll start off with something nice and simple, the LED. We know how to program an LED using blocks. We've done it lots and lots of times. So let's have a look at how we go about doing that in the code. On the Valiant robot, so we've got this really big LED at the back of the robot. And in our circuit, that's actually plugged into pin 13. So let's have a look. This is the block-based program that we would have before. And in our forever loop, we can actually set it to turn on, wait for a second, and then turn off that particular pin. So setting it to high and low turns it on and off. And then we're waiting a second. So it's going to flash on and off each second. But what's this look like in the text? Well, our forever loop matches up to this void loop block. And this set pin 13 to high maps onto this digital write, all one word, digital write. And then in round brackets, we've got 13, which matches onto the pin that we were selecting in the block, comma, high, which matches onto the high-low that we were selecting in the block, closing round bracket, and then this semicolon at the end. So for setting the pin to high, setting the LED to turn on, we now have this digital write, 13 high, closing semicolon. Let's have a look at the delay. So for the delay, we want to wait for 1 second. Now in the blocks, we have the keyword, instead of wait, it's delay. And the timing, rather than being in seconds, we could actually change it in this drop-down list from milliseconds or seconds. Here, the number is always going to be in milliseconds, and there's 1,000 milliseconds in a second. So if we wanted to wait for 1 second, then we have to tell this to wait for 1,000 milliseconds. So the full line becomes delay, telling it to wait. And then in round brackets, the duration we want to wait for. And then we've got the semicolon at the end of the line. And essentially repeating that for setting it to low instead of high for this flashing off. So let's have a bit of a closer look at what we've got here. So much like we had loop, this is actually digital write. It's a predefined function name. Same for delay, that's a predefined function name that we're actually using. But don't worry about what that means too much. For that function though, we have some numbers or some what we call parameters, some details that we can send to that function to customize the behavior of it each time. So here we're sending the parameters 13 and high, and that's telling you which pin to use and whether to set that to high or low. And these are instructions or statements that we're sending to the computer. And for the computer to know that it's the end of that instruction, that individual line, individual block on the left-hand side, we actually have to add this semicolon. And you'll find that on the keyboard just to the right of the L key, typically. It's this little semicolon, a dot over a comma. And so each of these lines between the curly brackets has a semicolon on it. Now, although there's nothing in the on start block when we're when we're setting these pins, we do actually have to add a little bit more on the text-based side in order to get this to work. And this was magically added for us when we were using the blocks on their own. But what we have to do before we can actually set this pin to high is we actually have to tell the Arduino that we're going to be using this pin 13 as an output pin. So remember that some pins are used for input and some pins are used for output. For the Arduino, we need to specifically tell it actually in advance of using that pin that we are going to be using it for input or output. So in our setup function, which was the equivalent of the on start before, we need to tell it to put a particular pin in the output mode. So for pin 13, we want to set its pin mode to output. And because it's a line between the curly brackets as an instruction for telling the computer what to do, we need to also end that with another semicolon. So, camel case. Now you may have noticed that those function names didn't have any spaces in them. If we have a look back at those, we've got things like digital write, pin mode. These are multiple words that we would normally separate out and put a space in between them. But the computer really doesn't like spaces in function names or variable names. Now, some of you also had problems last year when the blocks let you define a variable which had spaces in, but then when you actually tried to use that variable later, it caused problems. And that was because of the space in the name. So as programmers, we look for alternatives to be able to describe what it is that something's doing using multiple words, but without including that space. And one of the most common approaches to doing that is something that we like to call camel case. And in camel case, we essentially have lots of humps in it, lots of humps as we go along, because each new word, instead of a space between each new word, we start each new word with a capital letter. So hopefully you can actually read this sentence at the bottom without too much difficulty, because each new word is starting with a capital letter as we go along. So camel case starts each new word with a capital letter. And using that, we can actually have these longer names that are a bit more descriptive, because it's useful to have variable names that describe what it is that they're actually representing, but without having to worry about any spaces in those names. And of course, there's the semicolons. You'll get used to using a lot of semicolons, but we have to use them in the right places. And essentially, we need a semicolon when we're giving a specific instruction to the program, telling it to do something. So these go on the individual lines between the curly brackets, but not on the line just before the curly bracket. And you'll most likely see messages about missing semicolons at times. You'll get used to remembering to put them in, and soon you'll be putting them in everywhere, perhaps more than necessary, and then you'll have to remember to take them out. So let's have a look at another component, the LDR, or the photoresistor from Tinkercad. And on the Valiant robot, we've got quite a big, if you were at the challenge day, you might have seen it, the photoresistor mounted at the front of the robot. And that is plugged into pin A0. So remember, we've got some analog input pins on the Arduino, and we're specifically using A0 here. Now, if we were programming this in the blocks, it would look something like this. What I've done is I've created a variable here, and I'm reading using the read analog pin A0 and setting the value of the input pin to the reading from that analog pin. And then printing out the value to the serial monitor and it's printing it with a new line. And then there's a half-second delay or a little wait at the end of the forever loop before it repeats that over again. So let's look at what that will look like in the text. Well, our forever loop, void loop, with the curly brackets and instructions inside those curly brackets. So we've got our input value, which we're using this equals sign, this single equal sign, to assign the analog reading from pin A0 to our input value variable. And we're finishing it with that little semicolon. For printing to the serial monitor, we then have this slightly more complex line of serial.print value, serial.println, and then in round brackets the value we want to print, which is our variable input value, closing brackets, semicolon. And then we've got our little wait at the end. This time we're only waiting for half a second, so that's 500 milliseconds. So just to repeat, we've got our variable input value. We're using this single equal sign to assign the value on the right-hand side to the variable on the left-hand side. So we're assigning the reading from this pin, which is an analog pin, on A0, and we're assigning that to our input variable. And then we're using this serial monitor, serial.println, to print out the value from it and then wait for a little while. But there is a little bit more that we need to do before this will actually work. So for example, for the input value, we need to create that variable first of all. So remember when in the blocks before you could use a variable, you actually had to create it. And we often encouraged you to set an initial value for that in the onStart. I didn't do that here, but it is automatically doing that for you in the blocks when you're programming the Arduino blocks. So we need to create a variable, and this can actually go before the void loop or the void setup. Go at the top of your program. So here I've got an input value that I've created. I'm defining the variable, and it's actually got this word int in front of it, and I'll explain what that means in just a moment. And I'm giving it an initial value, so I'm assigning it, so using this single equals, the value of 0, and is an instruction for the computer, so I'm finishing it with a semicolon. But remember, we also need to do a little bit inside the void setup. So the first thing we need to do in here is tell it the pin mode for the pin that we're using, to make it quite clear that we're using that particular pin and we're using it as an input pin. In reality, we can only really use A0, but it tells it, the computer, that we are going to be using pin A0 as an input. Now, for this serial monitor, we also have to do a little bit more work to get that working, that started for us. There's this little startup line. It's like a magic instruction that we need to execute. We need to run this line in order to make the serial monitor available. And that is called serial.begin. And then in round brackets, we have this magic number 9600. Now, I won't say exactly where that magic number comes from for now, but just to try and remember that if we want to use a serial monitor, then before we can actually print anything out, we actually have to begin the serial monitor, and we have to give it this particular magic number to get it started and working properly. So let's have a look at that int variable slightly more closely. Now, when we're defining our variables, so in this case our input value, we also need to specify what type of data it is going to hold. So we're going to be creating some variables, and we can actually specify the type of information, so the type of value that they will be storing. and then we can modify that value within that particular data type later on. Now, the int input value is making use of this int data type, and that's short for integer. That's basically your whole numbers. So 0, 1, 2, 3, 4, 5, and so on. So we can have a whole number. If we want just want a whole number, then that would be this int data type. Don't worry, don't panic about this too much. You'll get a lot of practice with these, and they'll become second nature as we go through the term. There's some other data types that I won't worry about too much, more just so that you're aware that other data types do exist. But if we want data types with, or if we want to be able to hold numbers that have decimal places, so a bit more precise, then that's actually called a float, for a floating point number, where there's a decimal point in there that can shift up and down depending on the size of the number. We also have a bool, short for Boolean, which can be true or false. And to some extent, that's like your high or low for the digital pins. We can have individual characters. So this char here is short for character. And they're actually inside these single quotes. And you note that we can actually have numbers in there, but if they're inside single quotes, then they'll be recognized as characters rather than as ints. And we can also have longer bits of text, and they're called strings, so stringing multiple characters together into one long line. And they're in double quotes, so rather than having the single quotes, we've got the double quotes. And so we can have multiple words, including numbers. If we have a number in double quotes, it'll be recognized as a string, not as an int. So don't worry about those too much, just to have a better understanding of what this int is meaning. So when we have our int input value equals 0 here, we're creating a variable that can hold whole numbers. There we go. So when we want to create a variable, we need to specify what data type we're using. Most of the time we'll be using ints, but sometimes we will use something slightly different. We want to give it a meaningful variable name. So we want to actually say something about what it's going to be holding. Calling a variable spaghetti is not very meaningful unless it really is actually going to be holding spaghetti. And so we want to give it something that will tell the person reading the code a bit more about what that variable is going to be holding. And we can assign it an initial value. It's good practice to do that, but it is actually optional. When we then want to modify it, we can specify, so we need to refer to a particular variable that we want to modify, so refer back to its name. And we then use this assignment operator, this single equals, and it'll be important to understand why I'm referring to it as a single equals next week when we start to add other similar symbols in. But this assignment operator, the single equals, and then we can give a value on the right hand side of that assignment operator to the value we actually want to assign it to. So this could be some expression. We could add 3 plus 5. We could take the reading from a sensor, and we can assign that to the value of the variable. So a couple more examples of variables. We can create variables to hold pin numbers, which pin different components are plugged into. So for example, int LDR pin equals 13. And then we can make use of that when we're reading and writing from the pin. We've created our int input value equals 0. And for that input value, we can set it equal to some sum on the right hand side. So we could be adding on to the existing value for the variable. So in this case, we're taking the existing value of input value, adding 5 onto it, and then assigning the result of that sum back into the variable. And because this is actually a surprisingly common thing that we want to do with variables, so in the block form you'd have a change value, that actually has a shorthand version, an abbreviated, simpler to write version of plus equals 5. And that's essentially the same as writing input value plus 5. And there's also an example of using a Boolean as well. So we could initialize a Boolean with value false, and we can change it to be true at a later date. So just to finish off with the variables, we can print out using the println, serial.println, our input value. We can also print out text as a string to our print. Well, there's two different versions of the print. So if you remember in the blocks, it had with a new line or without a new line. That maps over to serial.print or serial.println. And this serial.println or println is short for print line. And that will add the new line at the end of it. So print your value and then go on to the next line. Or you can actually print multiple things onto a single line by using this serial print, and that won't move the cursor. It's like not pressing the return key at the end to typing a word. So you can then carry on printing multiple things onto the same line until you add this println, and then it will go on to the next line. And so that would look like, for this particular command's LDR reading, and then whatever the value was. So last thing for this introduction, which I know has been quite long for you this week, and that's to be aware that you're going to come across lots of bugs in your programs, lots of nasty red error messages. And unfortunately, 10% of programming is writing the code. About 90% is working out why it doesn't work. So when we're writing our text-based programs, they very, very rarely work first time. I think it's incredibly rare. It's the simplest of programs you might be able to write and it will work first time. But the majority of the time, even I write programs, I spend most of my time debugging my programs. Most of the time when you first write a program, there's going to be bugs in it. And so we have to spend a bit of time trying to work out what's gone wrong and why it isn't working. And there's two categories of bugs that we might come across when we're writing our programs. And the first is the bugs that won't even allow our program to run. And we refer to those as compiler errors. So essentially before a program can even run, and this is pressing the simulate button in Tinkercad, then it checks our program for various errors. It can only check for certain things, it can't check for everything. But it will check our program for certain types of errors, and this can be things like missing brackets, missing semicolons, spelling mistakes in variable names. And it will tell us. It will tell us in a not necessarily easy to understand way, unfortunately. It would be nice if the error messages were a bit more useful at times, but we'll give you some practice actually understanding what some of those error messages mean and how to recognize them and how to fix them. Because, as I say, we do get lots of errors when we're writing our programs. They're just too complex. But there's also some runtime errors that we can come across. So once we've got our program actually running, we know that it doesn't always do what we want it to do. And we had the same with the blocks as well. It didn't always do what we wanted it to do. And my thing with runtime errors is computers do exactly what we tell them to do. It's just we haven't always told them what we actually want them to do, or we haven't told them in the way that they can understand what it is that we want them to do. So there's the errors that the compiler can't tell us about that we will then need to fix. But before we get to those, we will come across some of these nasty compiler errors first. So things to remember for this first week. We're moving into the text-based programming, and the computer is incredibly fussy about the way in which we write our programs. One of the biggest things to be aware of is the capitalization is essential. So if you have different capitalization in to what it's expecting, if it's for one of those special named predefined functions, loop and startup, it has to exactly match that writing. If you start with a capital letter, it won't recognize it. And same for the variable names. You have to write them exactly the same each time. If they're spelt slightly differently, sometimes different capitalization, then it won't match up. The computer is incredibly fussy about that. Brackets, they always pair up. So if you're getting errors about brackets, don't just go throwing in random brackets, but try and count the pairs, make sure they are actually matched up. And next week I'll talk a bit more about this, but we can use spacing or indentation in order to help us keep track of brackets, in order to help make sure that they are always paired up. And then finally, those single line instructions or statements always end with a semicolon. And that little annoying semicolon that you have to add at the end of the line, very easy to forget, but it will complain without those. So there we go.